Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, the Stern-Gerlach experiment, conducted in 1921 by Otto Stern and Walther Gerlach, stands as a cornerstone in the development of quantum mechanics. This work, titled Experimental Demonstration of Space Quantization, presented compelling evidence for a phenomenon previously only theorized, the quantization of angular momentum. This essay undertakes a detailed examination of the original publication's claims, evaluating its methodology, assessing the presented evidence, and contextualizing its lasting impact within the scientific community. The analysis proceeds on a section-by-section basis, scrutinizing the experiment's design, the results obtained, interpretations offered by Stern and Ger. Section 1 Introduction and Theoretical Background. The introductory section of Stern and Gerlach's paper lays the foundation by summarizing the existing theoretical framework concerning atomic magnetic moments. They explicitly state the prevailing understanding that atoms, possessing a magnetic moment due to the orbital motion of their electrons, should align themselves in a magnetic field. Classical physics predicted that these alignments would be continuous, with atoms orienting at any angle relative to the applied field. The paper acknowledges the contributions of earlier researchers, particularly regarding the Bohr-Sommerfeld quantization rules. Stern and Gerlach then carefully articulate the fundamental theoretical claim under investigation, whether the magnetic moments of silver atoms are indeed spatially quantized, meaning they can only align in discrete directions relative to an external magnetic field. The boldness of this proposition is difficult to overstate, given its departure from the classical continuum. Evaluating this introductory section, one discerns a clear and concise presentation of the theoretical landscape. The authors successfully position their experiment as a direct test of a fundamental question posed by the emerging quantum theory. Their careful acknowledgement of prior work establishes a strong foundation for their own contribution. Section 2 Description of the experimental apparatus. This section provides a detailed account of the experimental setup. Stern and Gerlach meticulously describe the apparatus, consisting of a silver oven producing a beam of silver atoms, a collimating slit system to narrow the beam, and a specially designed magnet creating a highly inhomogeneous magnetic field. The critical aspect here lies in the magnet's configuration. It generated a magnetic field with a strong gradient, intentionally designed to exert a force on the silver atoms that was proportional to the component of their magnetic moment along the field direction. The paper painstakingly details the geometry of the magnet poles, explaining how they achieved the required field inhomogeneity. They also describe the detection method, whereby the silver atoms deposited on a glass plate, forming a visible trace. Assessing this section, the level of detail provided enables replication by other researchers. The careful consideration given to the magnetic field gradient and the beam collimation demonstrates a rigorous understanding of the experimental parameters. The design choices reflect a clear attempt to isolate and measure the influence of space quantization, attempting to minimize other potential confounding factors. Section 3 Experimental Procedure and Data Acquisition. Stern and Gerlach meticulously outline the experimental procedure, emphasizing the care taken to eliminate potential sources of error. They detail the process of heating the silver oven to generate a consistent atomic beam, the precise alignment of the collimating slits, and the evacuation of the apparatus to minimize collisions between silver atoms and air molecules. They describe the duration of the experiment, including the time needed to deposit a sufficient amount of silver onto the glass plate for observation. Additionally, they mention the precautions taken to maintain a stable magnetic field during the experiment. A thorough examination of this section reveals the commitment to rigorous experimental control. The authors demonstrate awareness of potential systematic errors and implement procedures to mitigate their impact. The detailed description of the data acquisition process lends credibility to the subsequent presentation of the results. The precautions taken to ensure a well-defined atomic beam and a stable magnetic field underscore the author's commitment to obtaining accurate and reliable data. Section 4. Presentation of results. The observed splitting of the silver beam. This section presents the core experimental finding: the splitting of the silver beam into two distinct traces on the glass plate, contrary to classical predictions, which would have produced a continuous distribution of silver atoms across the plate. Stern and Gerlach observed two well-separated lines. The paper includes a photographic reproduction of the observed pattern, providing compelling visual evidence for the quantization of the magnetic moment. The authors explicitly state that this result directly supports the hypothesis of space quantization. They acknowledge the limitations of their resolution, noting that the two lines were not perfectly sharp. The clarity of the presentation is noteworthy. The inclusion of the photographic image allows direct visual verification of the key finding. The author's careful wording suggests an awareness that the observed splitting, while compelling, might be subject to interpretations beyond simple space quantization. The visual and textual presentation of the results constitutes the strongest piece of evidence within the paper. Section 5. Discussion and interpretation of the results. Stern and Gerlach delve into the interpretation of their experimental findings. They acknowledge that the observed splitting directly contradicts the classical prediction of a continuous distribution. They argue that the two distinct lines provide strong evidence for the quantization of the component of the silver atom's magnetic moment along the direction of the magnetic field. They connect their results to the Bohr-Sommerfeld quantization rules, suggesting that the magnetic moment of the silver atom is quantized in such a way that it can only align in two distinct directions relative to the field. The authors also address potential alternative explanations for the observed splitting. They consider the possibility that the splitting could be caused by collisions between the silver atoms, but dismiss this explanation based on calculations showing that the atomic density in the beam was too low for significant collisional effects. They further discuss the potential influence of the Earth's magnetic field, concluding that its effect would be negligible compared to the strong gradient field generated by their apparatus. A thorough evaluation of this section indicates that the authors proactively engage with potential criticisms and alternative interpretations of their data. Their careful consideration of collisional effects and external magnetic fields strengthens the argument for space quantization. The connection to the Bohr-Sommerfeld quantization rules provides a theoretical context for understanding the experimental results. This section successfully argues for the validity of the space quantization interpretation while acknowledging potential Section 6. Refinement of theory and later developments. While not explicitly present as a section in the original Stern-Gerlach paper, a critical evaluation necessitates considering its implicit implications and subsequent refinements. The initial interpretation faced challenges. The simplistic Bohr-Sommerfeld model predicted an odd number of orientations, not the observed two. This discrepancy highlighted the limitations of the early quantum theory. The later introduction of electron spin, spearheaded by Uhlenbeck and Goudsmit, clarified the picture. The silver atom's single valence electron possesses an intrinsic angular momentum, or spin, which is quantized. The spin magnetic moment is responsible for the observed splitting. This refinement doesn't invalidate the core finding of Stern and Gerlach, but rather provides a more complete theoretical explanation. Examining these later developments, it illuminates how scientific understanding evolves. The Stern-Gerlach experiment acted as a catalyst, prompting further theoretical advancements that ultimately refined our understanding of atomic structure and quantum mechanics. The initial interpretation, while not entirely accurate, provided a crucial stepping stone toward a more complete and nuanced picture. Section 7. Sources of error and limitations in the original experiment. A comprehensive evaluation demands a critical assessment of potential sources of error and limitations inherent in the original Stern-Gerlach experiment. The resolution of the lines was not perfect, and the broadening could be attributed to several factors. Imperfections in the magnetic field gradient, thermal motion of the silver atoms, and scattering within the atomic beam could all contribute to line broadening. The vacuum wasn't perfect, meaning residual gas could interact with the silver beam. While Stern and Gerlach attempted to address these factors, their instrumentation possessed inherent limitations. Furthermore, the detection method, relying on visual observation of the silver deposit, introduced subjectivity. The density of the silver deposit could vary, affecting the perceived intensity and width of the lines. Evaluating these potential limitations, it acknowledges the inherent challenges of conducting precision experiments. The authors were aware of these limitations and attempted to mitigate their influence. The imperfections do not invalidate the fundamental result, but they do highlight the need for careful interpretation and further refinement of the experimental technique. Section 8 Impact on quantum mechanics and subsequent experiments. The Stern-Gerlach experiment had a profound impact on the development of quantum mechanics. It provided the first direct experimental evidence for space quantization, a concept that was previously only theoretical. This experimental verification helped to solidify the foundations of quantum mechanics and encouraged further research in this area. The experiment inspired numerous subsequent investigations. Researchers adapted the Stern-Gerlach technique to study the magnetic moments of other atoms and molecules. The experiment also served as a prototype for more sophisticated experiments involving atomic beams and magnetic fields. It plays a crucial role in quantum computing. The experiment's influence extends far beyond its immediate findings. It demonstrated the power of experimental validation in confirming theoretical predictions and served as a catalyst for further discoveries in quantum mechanics. Section 9 Alternative Interpretations and Contemporary Critiques. While the interpretation of the Stern-Gerlach experiment as direct evidence of space quantization is widely accepted, it is essential to acknowledge potential alternative interpretations and contemporary critiques prevalent at the time. Some scientists questioned the validity of the experimental results, suggesting that the observed splitting could be attributed to factors other than space quantization. They argued that surface effects, collisions within the atomic beam, or imperfections in the magnetic field might contribute to the observed pattern. These critiques prompted further investigation and refinement of the experimental technique. The critiques highlight the importance of skepticism and critical evaluation in scientific inquiry. The persistence of the space quantization interpretation. Despite these challenges, speed to the robustness of the experimental evidence and the theoretical framework support. Section 10 Reconstruction and modern iterations of the experiment. Reconstructing the Stern-Gerlach experiment in a modern laboratory setting presents unique challenges and opportunities. Contemporary iterations benefit from advancements in technology, including more powerful magnets, improved vacuum systems, and more sensitive detection methods. Modern experiments often employ laser-cooled atoms to reduce thermal motion, leading to sharper and more well-defined splitting patterns. Furthermore, sophisticated imaging techniques allow for precise measurement of the atomic beam profile. The ability to manipulate and control individual atoms has opened entirely new avenues of investigation based on the principles demonstrated in the Stern-Gerlach experiment. Comparing the original experiment with modern iterations highlights the remarkable progress in experimental physics. The basic principles remain the same, but the precision and control achievable in modern experiments are vastly superior. This allows for more detailed studies of atomic and molecular properties, as well as the exploration of more complex quantum phenomena. Section 11 Connection to spin and angular momentum. The Stern-Gerlach experiment, while initially interpreted in terms of orbital angular momentum, finds its most profound connection with the intrinsic angular momentum of particles, known as spin. The observed splitting of the silver beam into two distinct components directly reflects the two possible spin states of the silver atom's valence electron. This connection to spin is fundamental to understanding the behavior of particles in magnetic fields and has far-reaching implications in various fields, including particle physics, condensed matter physics, and quantum computing. The spin angular momentum exhibits quantization and responds to magnetic gradients. Understanding the connection between the Stern-Gerlach experiment and spin angular momentum provides a deeper understanding of the fundamental nature of particles and their interactions with electromagnetic fields. This connection is essential for comprehending a wide range of phenomena in physics and related disciplines. Section 12 Technological Applications and Contemporary Significance. The principles underlying the Stern-Gerlach experiment have found numerous technological applications in contemporary science and engineering. Atomic clocks, which are used in GPS systems and other precision timing applications, rely on the manipulation of atomic energy levels using magnetic fields. Magnetic resonance imaging (MRI), a powerful diagnostic tool in medicine, utilizes the interaction between nuclear spins and magnetic fields to create detailed images of the human body. Furthermore, the Stern-Gerlach principle is being explored in the development of quantum computers. The spin of an electron or other particle can be used as a qubit, the basic unit of information in a quantum computer. The Stern-Gerlach experiment serves as a testament to the power of fundamental scientific discoveries. The seemingly abstract phenomenon of space quantization has led to a wide range of technological innovations and have transformed various aspects of modern life. Section 13 Further developments and refinements in technique. The experimental technique pioneered by Stern and Gerlach has undergone significant development and refinement over the decades. The introduction of molecular beam epitaxy, a technique for growing thin films with atomic precision, allows for the creation of materials with tailored magnetic properties. Furthermore, advancements in laser spectroscopy have enabled researchers to probe the energy levels of atoms and molecules with unprecedented accuracy. These techniques have extended the reach of the Stern-Gerlach principle, allowing for the study of increasingly complex systems. It has also enabled for the creation of novel materials with unique magnetic properties. Studying these refinements allows a deeper understanding of the evolution of experimental physics. Section 14 Analysis of mathematical frameworks used for data interpretations. The interpretations surrounding the Stern-Gerlach results relied upon mathematical frameworks to substantiate claims around the observed data. The initial framework adopted centered on the Bohr-Sommerfeld quantization, postulating atoms orient themselves within magnetic fields according to quantized spatial orientations. However, interpreting such spatial quantization through the vector model implied silver atoms align at set angles relative to the applied magnetic field. This alignment is directly attributable to the atom's magnetic moment. These mathematical models enabled scientists to predict and explain the splitting pattern seen in the experiment, providing a rationale and quantitative explanation. The mathematical framework of quantized angular momentum further supported the observed phenomena. These frameworks not only allowed the fitting of data to theoretical values but also advanced theoretical understanding of atomic behavior in magnetic fields, leading to deeper explorations into quantum mechanics. Section 15 The original paper's style, rhetoric, and academic reception. The original Stern-Gerlach paper is characterized by its meticulous detail, clear prose, and cautious interpretation of results. The authors present their findings with a degree of scientific rigor, acknowledging potential sources of error and alternative explanations. The paper's rhetoric is persuasive, but not dogmatic. Stern and Gerlach avoid making overly strong claims, instead emphasizing the tentative nature of their conclusions. This cautious approach likely contributed to the paper's positive academic reception. The paper was widely cited and discussed in the scientific community, and it played a key role in shaping the development of quantum mechanics. The academic reception highlights the enduring impact of the experiment. Conclusion: the Stern-Gerlach experiment as presented in the original 1921 publication, represents a watershed moment in the history of quantum mechanics. The meticulous design of the experiment, combined with the compelling visual evidence of space quantization, provided strong support for the emerging quantum theory, while the initial interpretation of the results required refinement with the later discovery of electron spin. The fundamental finding of quantized angular momentum remains a cornerstone of modern physics. The experiment's enduring significance lies not only in its experimental verification of a previously theoretical concept but also in its profound impact on subsequent research and technological developments. The detailed analysis of the original paper reveals the careful experimental design, the rigorous data analysis, and the cautious interpretation that characterized this groundbreaking work. The Stern-Gerlach experiment offers an object lesson in the power of experimental science to challenge classical assumptions and to pave the way for new scientific paradigms. The enduring legacy of Stern and Gerlach extends far beyond the confines of their laboratory, shaping our understanding of the fundamental nature of matter and inspiring generations of scientists to explore the mysteries of the quantum world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.